In this course, we're going to learn chemistry from a bottom-up approach, starting with the most basic units, which is atoms. So we know that matter is composed of particles, small particles, and each of those particles has mass and volume. When those particles come together, either to interact with each other as to create new compounds such as molecules, or even just interact with each other when they're not even bonded, that will determine its physical properties. And so in our chemistry course, we're going to try to understand matter and its properties based off a bunch of different trends and fundamental ideas. So atoms are the most basic microscopic particle that is going to be the building blocks of matter. And when these atoms come together as either two or more atoms, this is called a molecule. And molecules are going to, because it has two or more things coming together, it's going to have a shape. We want to make sure we classify matter by both its composition, or what the particles are that make it up, and as well as its state. Is it a solid, liquid, or gas? And depending on these two things, that matter will have different properties. So when we think about the difference between solid, liquid, and gas, with spacing, solid is really tightly packed. Liquids, it's tightly packed, but not as tightly packed. And so we'll just say it's packed. And in gases, there's space in between. With particle movement, solids they're not moving, but they are vibrating. So they're not moving and translating in space, but there is some slight movement in vibration, where liquids and gas both have free movement, which causes the ability for flowing. When we think about shape, we want to think about both the volume and the shape that it takes. So for solids, it's a fixed volume and a rigid shape. So if I have an ice cube and I put it from one container to another, it's going to have the same volume and it's going to maintain its shape. Where liquid, it will also have a fixed volume, right? 100 milliliters is 100 milliliters, but it takes the shape of the container. So it's not rigid. And gas, it has a compressible volume, so it can expand and compress. And it also takes the shape of the container because it can move around. So a very classic example is water, right? Solid water, ice, it is fixed volume, it's rigid. Liquid, it can spill, right? Can flow, and it takes the shape of the container. And then water vapor, compressible, and takes the shape of the container. So I like this diagram because it helps to see the flow of how we classify matter. If there's one type of particle, that would be a pure substance. So this could be elements or compounds if it is just made up of one type of particle. And if it can be separated into smaller substances, then it would be a compound. If it can't, then it's an element. So an example of this might be I have helium versus water in a container. So helium, right, and water are both a pure substance. They show up as, right, we can drink pure water. There can be a pure helium tank. But I can break water down into hydrogen and oxygen, where with helium, it's already at its base level. So helium would be an element, where water would be a compound. If there's more than one type of particle, then it would be a mixture. Now we have to think about it. If I looked at it microscopically, would it be uniform throughout? So if the answer is yes, we'd call it homogeneous, because on the molecular level, and even just looking at it, we can't tell one thing from another, right? It just looks uniform. But if I was to go to the beach and grab some water from the ocean, I would see sand particles. I might see some plankton, right? I might see some other like rocks, and then I would see water. So that is not uniform throughout, because we can see with our eye and even more zoomed in that it is separate particles. So we're going to identify the statements as true or false. I want you to pause now, and then I will pull up the answers. All right, so let's think about it. Every molecule is a compound. So for a molecule, we know that a molecule from our very first slide was two or more elements together. And a compound is broken up into two types of elements. So every molecule is a compound. That's going to be false, because I can have a molecule such as a hydrogen, H2. It is a molecule because it's made up of two hydrogen atoms, but they're not two separate elements, so it is not a compound. Every compound is a molecule. This one, though, is true. Every compound is two or more types of elements coming together, so by default, it satisfies our molecule definition of two or more elements. A sample can be both an element and also a compound. So to be an element means it's in its pure state, and to be a compound means it can come apart. So this is false. A sample can be both a pure substance and a mixture. That is not true. If we look at the very first breakdown in our flowchart, you're either a pure substance or a mixture. So that is false. So if we look at the options here, circling whether things are whether these species are molecules, compounds, or pure elements. Let's just look at carbon as a whole. So carbon is just one carbon atom, so therefore it's not a molecule or a compound, but it is a pure element. It's on its own. When we look at nitrogen gas, N2, it is a molecule. It's made up of two or more atoms. It's not a compound because those atoms are the same, and it would be a pure element. So that is actually how nitrogen shows up in nature. Now water is a molecule because it's two or more atoms, and it's also a compound because those atoms are different, but it's not a pure element because it has two or more things. So you can't be both a pure element and a compound. Okay, so sulfur, it is a molecule because there's more than one atom, but they're all the same, so it's not a compound, and it is a pure element. This is how sulfur shows up. C6H12O2, this is a molecule for sure. It has many atoms, and there's more than one type, so therefore it's a compound and not a pure element. And then Fe, iron, it is not a molecule. It's just one element, and therefore it's not a compound, so it's just an element. Okay, so how do we start to learn a little bit more about what matter is made out of and its properties? Well, we're going to need to learn a little bit more about the scientific approach. The basis of it is based on making observations and trying to explain what they are and then testing that with an experiment. And it helps us to understand what works and what doesn't work, and that's all in data. So we're going to make an observation, right? So it could be you're walking outside, you see a rust-colored rock. That's your data. You might make some measurements. You might talk about its color, how hard it is, and describe it. Then you make a hypothesis. So you formulate your hypotheses. What do you think it is? Well, based off of my knowledge, that a coppery color on a rock kind of seems like it could be rust or iron oxide. So then I would need So this is what I think it would be based off of my life experience and the knowledge I know now. Then I'm going to try to do an experiment. And with that experiment, I'm going to do some kind of physical and chemical reactions to identify whether my hypothesis is supported. And then I'd also like to try to prove it wrong. And with my results, I might, as I do my experiment, I make more observations. I then continue more hypotheses. I might do another experiment until I'm pretty sure of what that rock is made out of. So when we do this scientific approach, we can formulate laws and theories. So just think in your own life, like, what is the difference between a law and a theory? So the definition of a scientific law is that it is a brief statement that summarizes past observations and predicts future ones. So this is all based off of experiments that have been done, and then, right, if I drop a rock, it's gonna fall. That is the law of gravity. It's just something that I see every time I drop a rock, it's going to fall at the same rate. And so I can use my past observation and predict my next ones based off of that, right? If I do it enough and I keep getting the same result, I can form a law. A law example is conservation of mass. So basically that says that mass is neither created nor destroyed. So lots of experiments have gone in and they started with an initial amount of matter. They did chemical reactions and the same amount of mass ended on the other side. So it always has happened, and so far it always will, as far as we're concerned. Where a theory is going to take a bunch of laws and it's going to try to pull them together and come up with a hypothesis or a set of hypotheses that kind of explains why those laws happen. So not just the what nature does, right? Not just the observations, but the why. It's trying to actually explain a phenomenon. So we could have also the law of the theory of gravity, gravitational theory. So we have the law that does all the predicting, but then the why behind it is also something to look into. So we have Dalton's atomic theory we'll talk about in this chapter. The Big Bang theory is one, right? At this point, with the data we have, this is what we can kind of assume is going to hold true because they are validated by experimental results. But these can never be conclusively proven because the more data we learn, we might get some new data, a new law that comes up that contradicts our theory. And so then we have to adjust the theory and come up with something better with the new data we have. So thinking about what is the difference between a law and a theory, right? A law is truth, where theory is speculation. I think that's a big no, right? It's much more than a speculation, right? A lot of thought and a lot of data and laws go into theories, so it's not just like a guess. A law summarizes a series of related observations, okay, while a theory gives the underlying reason for them. Okay, that sounds okay so far. So then a theory describes what nature does and a law describes why nature does it. Well, that's actually backwards, right? Because the laws describe the what and the theory explains the why. So it must be B. All right, a little bit of background quickly on the early ideas of matter. So Leucippus originally thought that matter was basically made up of small particles that were indestructible, but he thought that each of these atoms were different shapes and sizes that just kind of moved randomly. And I don't want to overshadow Democritus as well. Then Plato and Aristotle did not believe this at all. They basically thought that there was no smallest part, that you can keep breaking it down indefinitely or infinitely, and that matter was made out of the different quote unquote elements: fire, air, earth, and water. And then all the way into the 1700s, John Dalton gave other ideas that went back to Leucippus and started supporting some of those ideas and got a little bit more into the nitty-gritty. So he came up with the atomic theory of matter, which was composed of the law of conservation of mass, definite proportion, and multiple proportions. So in Dalton's atomic theory, the laws get explained through this. Basically, each element is composed of tiny, indestructible particles. And then we're going to call those atoms. Okay, so that's what Leucippus was thinking. He then explained that all atoms that are made out of a given element have the same mass and properties. Right, so carbon is carbon, hydrogen is hydrogen. And those properties are different from atoms of other elements, right? So carbon and hydrogen are going to act differently. When atoms come together, they combine in simple whole number ratios to form molecules. And when atoms of one element, when atoms react, there is an exchange of atoms on how they're bound together, but they cannot change into elements of another, or atoms of another element. That part basically just disproves alchemy. So here we have sodium, we have chlorine. They have very different masses and different properties, right? Gas versus solid. They come together into a ratio of 1:1 to create salt, which has different properties as well. And then in 1797, so let's just talk about these different properties. So 1797, we get Joseph Proust, and he helped come up with the law of definite proportion, which basically just says that when we have a sample, it doesn't matter how we got the sample, this sample is going to have the same proportion of the elements. So this is also called law of constant composition. So if I have 18 grams of water, I'm going to get 16 grams of oxygen and 2 grams of hydrogen. So the ratio is going to be 16 grams of oxygen over 2 grams of hydrogen. That's always going to give me a ratio of 8. And that would be the same if I had a sample of 20 grams of water, right? Or 1,000 grams. I'm always going to get this ratio. The law of multiple proportion, in my opinion, is a little bit more confusing. Basically says when I have two elements, we'll just be general and call them A and B, they form two different compounds. The masses of the element B with 1 gram of element A will always be expressed as a ratio of small whole numbers. So for example, well, let me go back into this. So I'm going to have, for every 1 gram of A, I could have 1, 2, or 3 atoms of B. So it would look like this. This is basically saying, from the atomic theory, right, they're going to combine in whole number ratios. So if I have carbon monoxide and carbon dioxide, I look at how much, right, it's made out of carbon and oxygen, both of them. And if I look at how much oxygen there is in carbon dioxide, for every 1 gram of carbon, it gives me that many grams of oxygen. And for carbon monoxide, for every gram of carbon, I have 1.33. So if I take the ratio of those two, I get 2.67 grams of oxygen over 1.33 grams of oxygen, and that gives me 2. In 1897, an important discovery was done by J.J. Thomson in the cathode ray experiments. So cathode rays are where you shoot, so you take a tube and it has a negative end and a positive end. And there is, it's basically evacuated in the middle. And they shot these particles from the negative side and it attracted over to the positive side. And so with lots of measurements that they did, they added in a magnetic field on either side of the particles and an electric field, and they were able to make really careful measurements. And what they noticed were that the particles traveled in straight lines. And that it doesn't matter what the cathode is made out of, that they are going to have the same composition. So their composition is independent from the source that they came from, and that they carry a negative electrical charge. So J.J. Thomson was able to adjust the magnetic and electric field and see how if I put a positive field here and a negative field on the other side, these beam of particles, these cathode rays, cathode particles would travel up and bend toward the positive side, showing another negative. And so lots of experimentation and adjustment of the voltage and magnetic field difference, he was able to measure the charge to mass ratio of these particles. So this is a factor, right, of two different variables, and he measured that it had a value of 1.76 times 10 to the 8 coulombs per gram. So for every gram of material that was used, this many coulombs was measured, and that is a charge unit. Here is a visual of this instrument. So we have the cathode ray tube. The cathode here is made out of a material, metal, and then the anode's on the other side. When a voltage is adjusted, then these particles travel through. You see this beam. Let me undo that. You see this beam here. So when J.J. Thomson, if you look down here, put an electric or magnetic field on near the stream of particles, then it would bend, and then he could measure them on this film on the end here. So the angle at which it bent with in proportion to the strength of the magnet and the voltage that was being applied, those calculations were able to be done. Again, the charge to mass ratio was 1.76 times 10 to the 8 coulombs per gram. So then there was another experiment in 1909, and in this experiment they were able to determine the charge of a single electron. How they did it was, they took an oil here, and they sprayed it through a partition that allowed those oil droplets to become very, very small through an atomizer. It went into this chamber. And then on the chamber, there was a barrier with a single hole poked through it, such that only a small amount of oil droplets would go through at a time. Then they shot radiation through the field of where the droplets were going to go through. Now this radiation was a type that formed ions. Now we know that ions cause a charge on a particle. And so all of these particles from this point on were charged. Due to the fact that there was a negatively charged plate on the bottom and a positively charged plate for that barrier, the researchers were able to adjust the voltage difference between those two plates. See how the particles, which now have a certain number of electrons on them, were able to either slow their fall, hover or even start rising up towards the positively charged plates. And through those careful experiments and the fact that they were able to determine the mass of the oil droplets from the microscope, seeing the radii and using the density, they were able to notice that the oil droplets carried a charge that was a ratio or a whole number multiple of the charge of an electron, which they were able to find out. So the value was 1.6 times 10 to the negative 19 coulombs. All of these particles had a charge that was a multiple of that. So if we use from Millikan's experiment, the charge of an electron, and from J.J. Thomson's, we found the charge to mass ratio, we could actually find out the mass of an electron. So let's do it. Notice in Millikan's experiment, we have a single variable, where in Thomson's we had a ratio of variables. So that's basically a conversion factor. So if we take Millikan's experiment of each electron has a charge of 1.6 times 10 to the negative 19 coulombs, and then we take the Thomson experiment that each coulomb, or the charge to mass ratio was 1.76 times 10 to the 8 coulombs per gram of material, we get that an electron weighs 9.09 times 10 to the negative 28 grams. And often we're going to need it in kilograms, so that will be 9.09 times 10 to the negative 31 kilograms. So all of these values will be provided for you, but you might need them in the future for some calculations. So now we know some about the atomic theory. We know about an electron, some of its properties. But how do those subatomic particles sit within the atom? The very first proposal was by J.J. Thomson himself, and it is called or known as the plum pudding model. He basically thought that in an atom there was a sphere of positive charge represented by the red there, and it was kind of like this is the pudding basically, and it's all dense, equally dense. And then he thought that there was these negative electrons that were just kind of plopped throughout like a plum. But one of the next great experiments was done in 1909 by Ernest Rutherford, and he was a student of J.J. Thomson. And in order to confirm that plum pudding model, he did this experiment. So what was done was that a really, really thin piece of gold foil was placed inside this chamber, and a source of alpha particles were being emitted. An alpha particle is basically the nucleus of a helium atom, which is 2 protons and 2 neutrons. And if you think of what gold is, if you look on the periodic table, you can see that gold actually has 79 protons and on average over 100 more neutrons. So it's a lot larger of an atom than this particle. So they would expect that if your model, the J.J. Thomson model, we have all of these, plum pudding examples of these atoms, these gold atoms, that there should be, a pretty evenly dispersed neutrons and protons in here, and our electrons evenly distributed. They should basically go all the way through and hit the other side of the partition and be detected on the detector. What was seen was quite different, though. There was a lot of those particles that did go all the way through and have basically minimal angle from its source, But the weird thing was, every so often, some of these alpha particles would end up being redirected back at large angles. This was surprising to the scientists. They did not expect that there would be any kind of bounce back. And in fact, 1 in 20,000 did bounce back, while many also were just deflected at an angle. But keep in mind, most of them did go straight through the foil. These deflections and bounce back particles were the atypical expectation. What was concluded was that most of the atom is contained of just basically empty space. Since most of the time the particles went straight through the foil, it must just be pretty empty, not a lot of mass in there. But there must be a very dense region of matter, and that is what they call the nucleus. So we now know that the nucleus contains the protons and the neutrons, and this is where the majority of the mass of an atom comes from, and it's really tightly held in the middle. And then a large part of the atom is the electrons, and electrons, while they have a charge, they have a very low mass compared to the protons and the neutrons, and so we can kind of consider them quote-unquote empty space. If the plum pudding model did hold true, those alpha particles should have gone straight through with no deflection, because it should have been an even uniform space. But because there was that deflection and bounce back, that's telling us that there's really dense matter in the center. And if you think about it, like we talked about on the last slide, a gold nucleus is really heavy. It has about like 179 atomic mass units, so subatomic particles here. And an alpha particle is just 4. It has 2 neutrons and 2 protons. So if you hit this tiny little thing and you manage to hit it at this really heavy thing, of course it's going to bounce back. But considering most of the time, because most of the volume is empty space, that alpha particle just went straight through. So ultimately, the atomic model that we have now is based off of all of these experiments put together. There are 3 parts to it. The first one is that the atom's mass, most of the mass and all of its positive charge is held in the nucleus, and that nucleus is a really small, dense space in the middle. Most of the volume of the atom is empty space, and it has these negatively charged electrons in there. Now at this point, we don't know what those electrons are doing, but we just know that they're making up most of the space and that they're negatively charged. And we know that for neutral atoms, there are the same number of negatively charged electrons on the outside as in the positively charged protons in the nucleus, meaning that number of electrons equals number of protons for a neutral atom. Here's a little review of their masses. This is the mass of these particles in kilograms. Notice mass of proton, mass of neutron, very similar. And then electrons about 10,000 times, about 1,000 times smaller. No, 10,000, yeah. And then here's their charges, relative charges to each other, and then the actual charges in coulombs. So you might be wondering, there's a lot going on there. How does this have to do with the periodic table, and what should I be keeping track of? Well, the most important number that tells you what an atom is the number of protons. This is the definition of the element. Okay, it defines the element. So whatever atom has 6 protons, that atom is always carbon. Whichever atom has 20 protons, that atom is always calcium. So calcium, by definition, has that. On the periodic table, you'll see the atomic number is that integer number, and then the chemical symbol is usually the bolded two-letter or two or one letter symbol, and then the name is below. You'll see other periodic tables have larger or have other numbers. We'll talk about those later. And then also note the way that the periodic table is arranged is such that elements that are in the same column here are they have similar properties called families. So I alluded to this a little earlier, but now we can fully teach it. Ions, so atoms on their own are neutral, but ions are the charged versions of their atoms. And how they become charged is either by gaining or losing electrons. So from the nuclear theory earlier, the number of electrons is equal to protons when it's neutral. But because atoms can gain or lose electrons, they can become ions. When an ion is positively charged, it's called a cation. I remember that because of this cute little cat. So cations are positive, right? And so this happens when an atom loses electrons, right? If we think about electrons are negatively charged, so if I take an atom, let's say I have 5 protons, 5 electrons. If I take away one of those electrons, now I have more protons than electrons, so I'd be positive. Metals all form cations. We'll talk about those later. Negatively charged ions are called anions, and they are, it's when an atom gains an electron or more than one. And so basically what can happen is out on the outside, if I have a neutral atom and I put an electron on, now I have 6 electrons, let's say. Now I have more electrons, so I'm going to have a negative charge. And you might be wondering, what about the protons? Why can't I just take away protons? Well, a couple reasons. One, the most legit reason is they're in the middle. They are stuck and they're happy in the middle. So it's really hard to remove those. So really hard to remove protons. 2, if I did remove the proton from the middle, well, so let's say I took away the 5, now I'm no longer that element. So if I remove it, I have changed the element that it was. So I'm not just an ion, I am also a new element. And we'll learn at the end of the second semester how you can have nuclear reactions where the proton does leave and it does create an ion. But the ions that we're mostly talking about is gaining or losing electrons. Isotopes, on the other hand, are elements that have a different number of neutrons. So ions means we change electrons. Isotopes means we have different amount of neutrons. Keep in mind, for both of these, we have the same number of protons. So I didn't change the element. I am the same element. But I could have a different number of neutrons. So for example, for hydrogen, most hydrogen is just a single proton in the middle and a single electron. There are some isotopes of hydrogen where I have a proton and a neutron, or a proton and 2 neutrons. It still has 1 proton, making it hydrogen, but it can get heavier with more neutrons. So isotopes, again, are the same number of protons, but different number of neutrons. The mass number we denote as A, and that is the number of protons plus the number of neutrons. So in here, the atomic number A equals 1. Here, A equals 2, because 1 proton plus 1 neutron. Here, A equals 3, because 1 proton and 3 neutrons. You can also see in an isotope notation, which we'll talk about later, that the mass number is shown up at this superscript area here. So here are the ways that we can represent isotopes. One way that you've already seen is by this first representation. We put the chemical symbol, X here, and then superscript the mass number. So again, that's number of protons plus neutrons. And then Z is a subscript, that is the atomic number, so number of protons. And that is sometimes not included because by knowing the chemical symbol, you can infer the atomic number. So for neon, there are 3 different isotopes. If we look at a periodic table, and I encourage you to get one out, we can see that neon has 10 protons. Its atomic number is 12. So all of these would have neon written, and it would have a 10 as its little subscript here. Now there are 3 isotopes. They have 10, 11, and 12 neutrons respectively. So I would need to find the mass number, add each of those numbers to 10 protons. So I would get 20, 21, and 22. And those are the ways we could represent neon. Another way is just including the chemical symbol followed by a dash and then the mass number. And that's usually how it's written if you were to read a paper or to talk about it. We might say neon 20 because that's its atomic mass, or neon dash 21, or neon dash 22. Same things, but just a different way that we can use it. So if we're going to practice this, here we have 3 different versions of carbon. We have carbon 12, carbon 13, and an anion of carbon 13. Here are an atomic view for you to see how it is. We have the nucleus here with 6 and 6, 6 and 7, and 6 and 7. Notice the atomic mass is pretty, it differs a bit. So if we look at this table here, we're going to fill out how many protons, neutrons, and electrons there are from the symbol. So number of protons, we know from the periodic table that carbon's atomic number is 6. So 6 protons all the way down. Now in carbon 12, we have protons plus neutrons is 12. 6 protons, so there must be 6 neutrons. And since it's a neutral atom, then the number of protons and electrons is the same, so there will be 6 there. For carbon 13, we have 1, it's a little heavier, so we have 7 neutrons. Since it is still neutral, we're going to have the same number of protons and electrons, so 6 and 6. And now when we have this anion of carbon 13, well, it still is heavy, so it still has 7 neutrons. But notice now I have an extra electron. Electrons are negatively charged, so I have an extra electron, so that means I have 7 electrons there. Notice they all have the same number of protons because it's all the same type of atom. But neutrons can vary and electrons can vary. Okay, on this problem, I want you to pause this video, try to determine the atomic numbers, mass numbers, and symbols, as well as how many protons, electrons, and neutrons there are in different isotopes. Pause here and I will show you the answer in a few seconds. Okay, so for chlorine, we can see from the periodic table that chlorine's atomic number is 17. So Z equals 17. Whoops. So I'm going to put a 17 down here on the subscript. Now it has 18 neutrons, so the mass number is going to be protons plus neutrons, so 17 plus 18. So this will be chlorine 35. All right. And so for this next one, we have chromium. It has 24 and 52. So we know from the atomic number here, that number of protons is 24. Since it's a neutral, the number of electrons is also 24. And number of neutrons is going to be the mass number, so 52, minus the atomic number of protons. And so that gives me 28. This one should have been pretty familiar. We have carbon we know carbon has an atomic number of 6, so 6 protons. In this one, there are 7 neutrons, so the atomic mass is going to be 6 plus 7, so 13. And number of electrons should be number of neutrons here, or protons, because it's a neutral atom, so it will also be 6. And this last one, we have potassium, 39 and 19. So potassium's atomic number is 19, which means its number of neutrons here is going to be the mass number minus 19, so 20 neutrons. And since it's neutral, the number of electrons is the same as the protons. So you may have noticed that on your average periodic table, we do see the atomic number and the symbol and the name, but we have this number that has a decimal. And we haven't talked about that yet because all of the things that we've been using have been integers, right? A full number of protons and neutrons. We don't have partial particles here. So what does that mean? This is actually called the atomic mass, not the mass number, and it is the average mass of all of the isotopes that exist for that element. So it's an a weighted average for that element's mass. So, if I have these 3 isotopes of neon 20, 21, and 22, well, the number that's going to be reported for neon, we can see, is closer to 20. This is telling me that there must be more of the neon 20 element than the 21 or 22 because it's averaged a lot closer to the value of 20. And we can see that neon 20 has an abundance of 90%, where neon 22 is about 10%-ish, and neon 21 is a lot smaller. So if we were to take the averages of all of those, the weighted averages of these different isotopes, then you would get the value found on the bottom of the periodic table. So let's just show you. What we do is we take the fraction of that isotope, multiply by the mass of that isotope, and you do that for you add that together with all of the isotopes. That's what this summation means. We're going to add those. So I'm going to take the fraction of isotope 1. So I'm going to take my percent abundance and divide by 100. I want it to be in the fraction form. So I'm going to have 0.9048 for that fraction times by that mass. Now, we would actually have the legit mass in grams per mole. We'll talk about moles later, or in AMUs, atomic mass units. But for the sake of this, I'll just do the number of the mass number, so 20 AMUs. Then I'm going to add that to the next abundance. So 0.27 divided by 100, I'm going to have 0.0027 times by 21 AMUs plus 0.0925 for that third isotope times by 22 AMUs. And so if we were to multiply that all together and add it, we get 20.1877 AMUs, and that's pretty close to what is seen on the periodic table. So let's actually practice it. In nature, we only have 2 isotopes of chlorine. So chlorine 35 is 75% abundance, and its mass is 34.97 AMUs, and chlorine 37 is about 25% abundant. And notice its mass is really close to 37, it's a little bit below, and 35 is really close to 35, but just a little bit below. So let's calculate that average mass. We are going to take 75.77 and make that in fraction, so divide by 100, 0.7577 times by its mass, 34.97 AMUs, plus the 24.23 divided by 100, so 0.2423 times by 36.97 AMUs. I encourage you to put that in your calculator. so you can see that practice getting that value, and you should get 35.45 AMUs. And you know where you can double check? Periodic table. In this one, we're going to do a little bit trickier. So I have gallium. It has two naturally occurring isotopes, gallium 69, here's its mass and abundance, and gallium 71. And we're going to use the atomic mass of gallium from the periodic table to determine the mass of gallium 71. So note, I'm going to use the equation average mass equals the fraction of one isotope times the mass of that isotope plus the fraction of the second isotope times the mass of the second isotope. I only have two here, so I could use that. Now, if we look at the periodic table, the average mass of gallium is 69.723 AMUs. So that's just from the periodic table. Okay, so let's do gallium 69. It has an abundance of 60.11. So if I put that in fraction form, it'll be 0.6011. And that mass it gives us is 68.9256 AMUs. Plus the fraction of the second one. Now you might be saying, it didn't give us the fraction. But you can determine, we know that there's 100% total, and one of the two things is 60.7. So we know that the abundance, the percent of the other one, is 39.89%. So I can divide that by 100 and get 0.3989, and then solve for the mass of the second one. So what we're going to do here is we're going to get a value right here. That's just a number. And we can subtract that whole number over. We're trying to solve for M2. So I'm going to get 69.723 AMUs minus 0.6011 times 68.9256 AMUs. And that equals 0.3989 times the second mass. So I'm going to take this value here, this whole number, you can plug that in your calculator, and I'm going to divide by 0.3989. And that should give me my second mass. And to double check, our mass should be really close to 71. And it is. The mass of that second isotope, gallium 71, is 70.92 AMUs. So a little bit of algebra there. The last section we're going to talk about in this chapter is the mole. So we've been dealing with atoms, and there's a lot of atoms. This is a basic particle here, and we can't see an atom with our naked eye. And so we want to talk about groups of these atoms, or of any object, right? If I want to talk about apples, if I have a lot of apples, I'm not telling you how many apples. I'm going to tell you how many dozens of apples. Or you might have a gross or a ream. We group things all the time. So the mole is, quote unquote, the scientist's baker's dozen. We know that a dozen is 12 things. Well, now you're going to know what a mole is. A mole is 6.02 times 10 to the 23rd pieces of a thing. So we could have a mole of marbles. We have a lot of marbles. A mole of sand, 6.02 times 10 to the 23rd moles of sand, or grains of sand, pieces of sand. This is called Avogadro's number. A lot of avocado, a lot of guacamole references here, but this is the person that it's named after. And this is the number of atoms that are in 12 grams of pure carbon-12. So it's the number. So you may be like, what am I going to use this for? How does this work? Basically, it's another conversion factor. Just like I could say 12 apples equals 1 dozen, I can say 1 mole of something is 6.02 times 10 to the 23rd things. So I can use it when I'm trying to convert between number of things and moles, which we're going to do the whole year in this class and in future chemistry classes probably also. So if I could either say I have 1 mole of atoms or molecules per 6.022 times 10 to the 23rd atoms. Or I could say flip it and do 6.022 times 10 to the 23rd atoms per 1 mole of atoms. And it just depends on where you're going. So if I want to know, if I have 2.54 moles of copper, I can calculate how many copper atoms I have. I'm going to start with the number I have, 2.45 moles of copper. So now if I want to, just like any other conversion, I want moles to cancel out on bottom and atoms to come up top. For the sake of your life for a while, the number 1 is always going to go with moles, and your number is going to go with the other thing. So 6.02 times 10 to the 23rd atoms. So if I was to take my moles, multiply by Avogadro's number, I get 1.48 times 10 to the 24 atoms of copper. Similarly, if I have a large number of atoms, right, 2.8 times 10 to the 22 silver, which is Ag, atoms, I want to find out how many moles I have. So I'm going to take that value. I want atoms to come up on bottom to cancel out and moles to come up top. So I'm going to always put 1 with moles and then 6.02 times 10 to the 23rd on bottom. So I should get 0.0465 moles of silver. The thing I want you to be careful on when you're doing these calculations is if you ever are dividing by Avogadro's number, making sure your whole number is by parentheses, so that way you never get a partial atom. If you ever get like times 10 to the negative 3 atoms or 10 to the negative 23 atoms, you know that's wrong because that's a really small fraction of an atom, and that's not going to be a thing that you're ever going to calculate or find. We're always going to have a whole number of atoms, so a large number, something greater than 1. So you might be wondering, okay, I know what an atom is, I kind of get what a mole is, but we don't weigh things in mole or have any measurements of moles that we use. But if I want to know how much of something I have, I normally weigh it or I take its mass. So we need another conversion factor to get us from something we actually know, which is mass and can measure, into this mole thing. So we will have something called the molar mass. And it is exactly what it sounds. It is the mass that we can measure on a scale of 1 mole of atoms of an element. So this is basically the same exact thing as the element's average atomic mass. Before we had it in atomic mass units or AMUs, but that can also be called grams per mole. They're not the same value, but they are equivalent. So 1 mole of anything is 6.022 times 10 to the 23rd items of that thing, but the masses aren't necessarily the same. So I could have like a dozen marbles and a dozen peas, right? But they're going to weigh a different amount. So that's where molar mass comes in. So for example, 1 mole of aluminum, always 6.022 times 10 to the 23 atoms of aluminum, but it weighs 26.98 grams. Where does that come from? We can actually find it on the periodic table. So if we look at the periodic table for carbon, 1 mole of carbon is equal to again, an Avogadro's number of carbon. But if we look at the periodic table, its average mass is 12.01 AMUs, which means it's 12.01 grams for every mole. Same thing with helium. Avogadro's number of helium is a mole, and it weighs 4.003 grams. So the molar mass of any element is a conversion factor that we can use to go between grams of something and moles. And then we could always use Avogadro's number to go from moles to atoms or particles in general. But this is able to get us from the mass to moles. And again, an AMU is the same as a gram per mole as far as conversions go. So let's calculate the mass in grams of 0.473 moles of titanium. So we're going to start with the number that we have, 0.473 moles, and I want to get to grams of titanium. So I can look on my periodic table and see that the molar mass of titanium is 47.867, and that's grams per mole. So I want to get rid of moles, so I'm going to put moles on the bottom, gram up top. Now, just like with Avogadro's number, the number in front of moles is going to be 1. So the value that's a non-1 number is going to, so this number here is going to go with the grams. 47.867 grams. So when we do the math, we do 0.473 times 47.867, and we get 22.64 grams. Okay, so now let's calculate the amount of carbon. So we want to find the moles of carbon in 0.0265 grams of pencil lead, which is pure graphite, quote unquote pure graphite. So 0.0265 grams of carbon is what we have, and we want to get into moles of carbon. So once again, I'm going to use a conversion, and we're going to look on the periodic table to see that a mole of carbon weighs 12.01 grams, so that's the molar mass. So we could do, we want grams to go on the bottom now, moles to go on top. We're going to put 1 in for the moles and put the value of the molar mass, 12.01 grams, on the bottom. So now I'm going to do 0.0265 divided by 12.01, and we get 40, whoops, nope, I lied. We get 2.21 times 10 to the negative 3 moles of carbon. All right, so now without calculation, we have these two scenarios. The first one, student A claims that 10 moles of carbon contains the same number of atoms as 10 moles of sodium. Is that correct? So this one is using moles to atoms. Okay, now in the second scenario, we have a student that claims 10 grams of carbon is the same number of atoms as 10 grams of sodium. So here we have grams going to atoms, but to do that we have to do moles first and then atoms. Okay, so we know that the conversion factor between moles and atoms is Avogadro's number, or N sub A, and that is a constant, right? 6.02 times 10 to the 23rd atoms per mole. So since that's going to be consistent between each of these samples, then this is correct. Our conversion factor from moles to atoms is Avogadro's number. It's a constant, so they'll be the same. But in the second one, we have grams to moles and then moles to atoms. Now the second step here, yep, it's the same conversion factor, Avogadro's number. But in this first step here, we are going to be using the molar mass. And so molar mass, capital M, it changes from substance to substance. So carbon's molar mass is 12.01, sodium's is 22.9, and so their not going to be the same number of atoms because they have a different molar mass. They weigh different. So now going on, and I think that was a really good segue here, because if I want to go from mass into number of atoms, which I might, or in the future, number of molecules and such, then I'm going to need to do 2 steps. Moles is basically my middleman. It's the one that I'm going to go to all the time. And a phrase I like to say is, when in doubt, you're going to convert to moles. So if I'm in grams here and I want to go 2 moles, then I'm going to take my grams. I'm going to want to divide by the molar mass, right? Because I want grams on the bottom, 1 mole up top. So that number, molar mass, big M, I'm going to be dividing by. And then if I want to go from moles to atoms, then I'm going to have, now my moles, I'm going to have 1 mole on the bottom, and Avogadro's number, ends up A, number of atoms, will go up top. So I would divide by molar mass here, and then multiply by Avogadro's number here. If I'm going backwards and I have number of atoms, I know this is going to look a little weird, I'm going to do the opposite. And I don't want you to memorize this, I just want to let your units guide you. So in this case, I want to go to atoms. Going backwards, I want atoms on bottom, 1 mole up top. So I would divide by Avogadro's number to get to moles. And then from moles to grams, I'm going to want moles on 1 mole on bottom to get rid of it. And then the molar mass amount of grams on top. So I'd multiply to go that way. So let's practice. How many copper atoms are in a penny with a mass of 3.10 grams of copper? So I want to find out copper atoms. All right, so we are in this phase where we need to get to moles. No matter what, we're going to moles. So I want my grams to go on bottom, and I'm always going to have 1 mole up top. So where can I find the amount of grams? Well, that is on the periodic table. So go find copper. Copper has an atomic number of 29. Its molar mass, though, is 63.55 grams. So we can calculate, we could stop there and be in moles, but we have one more step to do because I'm not quite at the ending. Now I want to get rid of moles. I'm going to put 1 mole on the bottom, and I want to put atoms up top. So the conversion between moles and atoms is Avogadro's number, 6.02 times 10 to the 23 atoms. So we'll take our grams of copper, divide by 63.55, multiply by Avogadro's number, and I get 2.94 times 10 to the 22 copper atoms. All right, this next one is a little bit of a trickier one. I have a situation where I have 9.21 moles of oxygen. Now, oxygen is a molecule that contains 2 oxygen atoms. So in this case, I want to know how many molecules are in the sample. So again, Avogadro's number isn't just for moles to atom, it's from moles to any number of particles. In this case, our particles are going to be these molecules. So I'm going to do 9.21 moles of oxygen, molecular oxygen. And I want to get into molecules, so I'm going to do my conversion. I want moles to be on bottom, molecules to be on top. So again, 1 is always with the moles, and then Avogadro's number gets me to those out of moles and into particles. And so if I multiply that together, I get 5.54 times 10 to the 24 molecules of O2. Now this is the part that gets a little bit, not necessarily trickier, but something where you have to think a little deeper. And now a conversion that we're going to use is that 1 molecule of O2, so 1 molecule, has this 2 atoms of oxygen. So I want to find out in that original sample, right, I have 5.54 times 10 to the 24 molecules we saw of O2. I want to find out how many oxygen atoms there are. So So now we could just use this conversion factor that 1 molecule of O2 is 2 atoms of oxygen. So I'm just going to multiply by 2. So I end up getting 1.11 times 10 to the 25 atoms. So this is just another conversion factor. So many ways we can use conversion factors. So let's do that in this longer one. I have 5.65 milligrams of magnesium phosphate. So this is a pretty complex molecule or compound. So I have 3 magnesiums and then phosphate, PO4 with 2. I want to find out how many atoms of phosphorus there are. So I'm basically trying to figure out how many of those atoms are in the sample. So starting with what we have, we're not going to get too overwhelmed. We're going to just take it one step at a time. Now, we don't know any conversion from milligrams into moles. And we know if we want to find atoms of phosphorus, then I'm going to need to use Avogadro's number at some point. And so I'm going to need to then use a molar mass to get out of grams. So let's go from milligrams to grams. We know that for 1 gram there are 1,000 milligrams. So now I'm in grams. Now that I'm in grams, I can go into moles. Grams into moles. And again, we know there is 1 mole for this substance. So now I need to find that molar mass. And we've only talked about molar mass for an atom, but we could do the same thing with a compound. And we're going to explicitly teach this in larger detail in chapter 3, but just as like a little heads up. So I have 3 magnesiums. So I'm going to take each of them and then I'm going to add it to the rest of the compound. So I have 3 magnesiums. Now notice phosphate, PO4, is this compound, but I have 2 of them. So I actually have 2 phosphorus atoms and 8 oxygen atoms in this compound. So I'm going to have to do 2 times phosphorus plus 8 times oxygen. So if we look at the molar masses, 3 times magnesium is 24.305 grams per mole, plus 2 times phosphorus's mass is 30.974 grams per mole. And then I have 8 oxygens, and each oxygen is 16.000 grams per mole. So we're going to take our calculators and add that up. 3 times 24.305 plus 2 times 30.974 plus 8 times 16. And I get the total mass. It's a big one. This is a big compound. 262.863 grams per mole. Great. So now that I have that big number, I know what will go on the bottom. Okay, now I'm in moles, and I want to get, now this is a whole molecule or a compound. So when I use Avogadro's number, 1 mole, I'm going to have molecule up top, or a compound. And so I can use 6.02 times 10 to the 23rd. Now that's just going to tell me how many magnesium phosphate molecules or compounds there are. But I need one more step, because for every 1 molecule here, there are 2 phosphoruses. So 2 atoms of phosphorus. So when I do all of that math, I'm going to do 5.65 milligrams divided by 1,000 divided by 262.863 times by Avogadro's number, and then times by 2. I get 2.59 times 10 to the 19 phosphorus atoms. That is a tricky one. That's a long one, and you're not expected to know how to do this until chapter 3. So now we're just going to do a little bit more practice with this. Again, going from grams to atoms or atoms to grams. So more practice going between these 3 different units. So here it wants to know how many carbon atoms, so immediately I can put that there, are in 1.3 carat diamond. So I'm going to put 1.3 carat here. And they're telling us that 1 carat equals 0.020 grams, and that is a conversion factor, which is great because I don't know carats to moles. So I'm going to be able to get out of carat and into grams. The number in front of carat is 1. The number in front of grams is 0.20. So now that I'm out of that, I'm in grams, I can go to moles. So grams are going to be on bottom, 1 mole up top. The molar mass of carbon is 12.01 grams from the periodic table. And then now we're in moles, but not quite in atoms yet. We need to go from moles into atoms. Since we're dealing with a pure carbon to begin with, we are not in a molecule here. We don't need to go to molecules, we can just go straight to atoms. Again, we have a 1 with the mole, Avogadro's number up here with our grouping. And so we're going to take 1.3, multiply by 0.2, divide by 12.01, and times by Avogadro's number. And you should get 1.3 times 10 to the 22 carbon atoms. Now for this next one, we have tungsten. Now, just so you know, tungsten is element W. Don't ask me why it's W. It has to do with old naming. You just have to kind of know. We are starting with 2.25 times 10 to the 22 atoms of tungsten. And I want to get to grams of tungsten. So we want to get out of atoms and into moles. Since we're already dealing with a pure element, we're not in molecules or anything, we are good. So again, 1 will go with moles, and Avogadro's number will come up here with atoms. Now that I'm in moles, I want to go to grams, so I'm going to do 1 mole and grams up top. What is the molar mass of tungsten? You're going to want to look at your periodic table. Take a quick peek. It is element 74 in the periodic table, and so we can see that its molar mass is 183.84 grams. So now when I take that number of atoms, divide by Avogadro's number, and then multiply by the molar mass, you get 6.87 grams of tungsten. Now, if you got some really, really large number, like 10 to the 45 or something like that or higher, that's because your Avogadro's number was not fully in parentheses, so make sure you do that. Okay, in this last problem, we're finding out how many oxygen atoms are in each sample, so a little bit of similarity to what we saw in the last slide. So we have, for all of these, 16 grams of either atomic oxygen, molecular oxygen, or ozone, and we want to find out how many oxygen atoms in all of these cases. Okay. So let's just start with the top one. Notice we are just in grams of oxygen. So I want grams to go away. I'm going to put it on the bottom, and I want to go to moles. Again, 1 mole. Now, just a single oxygen is 16.00 grams for its molar mass. So we'll be able to go from moles, now 1 mole on bottom, to atoms. Now notice this is a singular atomic oxygen, so we can go straight to atoms. 6.02 times 10 to the 23rd atoms. and done. So if we take that 16, divide it by 16, multiply by Avogadro's number, I get 6.02 times 10 to the 23rd atoms. Okay, now we have molecules in this case and this case. So we're going to have an extra step. Still going to be able to go from grams to moles using molar mass. Now I have 2 oxygens in this molecule, so the molar mass is going to double. I have 32.00 grams per mole. So now when I go from moles, I need to go to molecules because this is a molecule. So I'm going to have molecule of oxygen. So 1 mole has that many, 6.02 times 10 to the 23rd molecules of O2. So I have one more step to get to atoms. So for every 1 molecule of O2, I have 2 atoms of oxygen, right, due to that subscript 2 there. So I'm going to take 16 divided by 32 times by Avogadro's number times by 2. And notice you get 6.02 times 10 to the 23rd. Very similar. That's pretty interesting. So last one we're going to do, it's going to be similar, but now we have ozone, which has a larger molar mass. Its molar mass is 48.00 grams per 1 mole. Now again, we're going to go out of moles, but now into molecules. So 6.02 times 10 to the 23rd molecules of ozone. And now to get from molecules of ozone, O3, then there are 3 atoms of oxygen in there. So when we do that, it will also be 6.02 times 10 to the 23rd. So notice we start with the same mass, but we change the ratio from the atom to molecule. We would get the same amount of total atoms there. All right, these are your challenge problems for this chapter. It has to do with EPA and lead. Notice this is the type of problem you might see on a test. It's going to test you on one overall concept, but a variety of chemistry topics within it. So here we have the EPA sets limits on healthful levels of air pollutants. The maximum level that is considered safe for lead air pollution is 1.5 micrograms per cubic meter. So just as a reminder, for 1 gram, that equals 10 to the 6 micrograms. That will come in handy later. Micro, you can think of as like a millionth of a gram or a millionth of something. If your lungs were filled with air containing this level of lead, how many lead atoms would be in your lungs? So we are trying to find out how many atoms of lead, Pb, there are in your lungs. Keeping in mind, lead is Pb. Now, notice this number here is a conversion factor. It has 2 units. The only value that has a single unit is the lung volume, 5.50 liters. So that's what we're going to want to start with, since we want to end with a single unit. All right, so notice we have a volume here. The other place we have a volume is in our conversion factor cubic meter. So we need to go from liters, we need to get out of liters, and we need to go into cubic meters. Now, you might not know this off the top of your head, and honestly, I wouldn't know this off the top of my head, so you could look it up. If I was to do this on an exam, I would go, I'll just do it up top so you can see it. I would go liters to milliliters, and we know that 1 milliliter is a cubic centimeter, and then cubic centimeter to cubic meter. That's how I would do it in 3 steps. Now, because this is a challenge problem and we're going to work on it together, I'm just going to tell you that for every 1 meter cubed, and what you could find online, there are 1,000 liters. So we could get there. All right. So now we're in meters cubed. We could use our conversion factor they gave us. So we want meters cubed on bottom to cancel out, and we're going to have 1.5 micrograms up top. Okay, so we are in micrograms, but we even need to get to atoms. So we know that in order to, before atoms, there are moles, and before moles, we have grams. So we need to get over to grams. And again, I gave you that conversion. We want to get out of micrograms and into grams. There are 1,000,000 micrograms per gram. Okay, so now we can do what we've been practicing. So we want to get out of grams and into moles. We know that 1 mole is equal to 207.2 grams from the periodic table. That's the molar mass of lead. And then I can get out of moles, 1 mole on bottom, and get into Avogadro's number. I'm already dealing with, this is the amount of lead that's allowed in your lungs, or allowed in the atmosphere. And so we are dealing with an atom here. So I'm going to put Avogadro's number up top. And we have our final unit. So let's take 5.50 divided by 1,000 times by 1.5, divide by 1,000,000, divide by the molar mass, times by Avogadro's number. Make sure you put this in your calculator because it's important that you practice. And you should get 2.40 times 10 to the 13 atoms. Okay. So this next question, still following lead, but now we're dealing with abundance. So it says, naturally occurring lead has the following isotopic abundances. Using the average atomic mass of lead, what is the atomic mass of lead-206? So we have all of these different abundances here and the isotopes, but we don't know the atomic mass of lead-206. We know it should be about 206, but it's going to be a little bit off from that. So let's figure it out. So we found earlier that the atomic mass of lead was 207.2. So now what we can do, let me check if I have a more precise lead value we can use. Nope, 207.2 is what I got. Okay, so we know that the average mass for lead is going to be equal to the fraction of lead-204 times by the mass of lead-204 plus the fraction of lead-206 times the mass of lead-206, and so on. So we're going to fill that out. And remember, the fractions are going to be the percent abundance divided by 100. So we know that the average value of lead from the periodic table is 207.2. We'll do AMUs, but grams per mole also works. Equals the fraction of 204. So 204 is 1.4%, so that's 0.014 in fraction, and its mass is 203.9730 AMUs. Plus, I'm going to do this kind of, no, I won't do that. Okay, plus, the next one is lead-206. Its abundance is 0.241, because we divide by 100, times by the mass. We don't know what it is, question mark, plus the abundance of 207, which is 0.221 in fraction form, times by 206.9759 AMUs, and then plus the mass of lead, 208, or abundance, which is 0.524 times by 207.9766 AMUs. All right. So what I'm actually going to do right now is take this number, and this number, and add them up. So on my calculator, I'm going to do 0.014 times 203.9730 plus 0.221 times 206.9759 plus 0.524 times 207.9766. So what you get for those values, so overall here we have 207.2 AMUs equals 157.5770 AMUs plus 0.241 times our mass of our unknown. So now we can subtract that value over. So we're going to subtract 157.5770 AMUs, and we get 49.622 AMUs. All right, and that whole thing equals 0.241 times our unknown mass of lead, 206. So now to solve for that mass, we're going to divide by 0.241. And we get our mass is 205.9044 AMUs. And just concept check, should be close to 206, and if we round, it would be. So that is our final answer.